Now, from these examples, there certainly appears to be a relationship between gradient vectors and level sets of the functions. And we're going to express that in terms of a lemma, a formal lemma that says the following. At each point, the gradient vector is orthogonal to that point's level set and is oriented in the direction of maximal increase of the function. Okay, what does that mean? Pick a point, look at the level set that passes through that point in a small neighborhood of it. Then what we're claiming is that the gradient vector is orthogonal to that level set at the point, and furthermore, that it's pointed in the direction where the function is increasing most rapidly. Okay, well that seems reasonable, but how do you prove that? Here's what we're going to do. Fix a point A where f takes on a value c. Of course, that value is f of a. Okay, now choose a unit vector at that point A. Call it u. It can be any unit vector pointing in any direction you want. What I want to know is what happens when you look at the rate of change of the output of f by changing the inputs using this vector u. Okay, well, that's something we know, right? That uses the derivative as a matrix. That's the derivative of f times the vector u, and that gives us a numerical value. Now, there's a bit of new notation here. This is sometimes called the directional derivative of f along the u direction, because u is a unit vector. See a little bit later for a bit more on that notation. But here's the thing. That matrix, which is like a row matrix, times u is really the same thing as the dot product of the gradient vector with u. Well, I mean, so what? That's kind of obvious, just algebra, right? Oh, no. This is really important because we have a geometric interpretation for dot products. Taking a dot product of the gradient of f with a unit vector u is really orthogonal projection of the gradient vector onto the u-axis. That means as we spin u around, as we change all the different directions, then this rate of change of f in the u direction is changing. And in particular, when u is tangent to the level set, then f is not changing in that direction at all, which means the derivative of f times u is 0, which means the dot product of gradient of f of u is 0, and that means that the gradient vector is orthogonal to the level set at that point. And furthermore, when u points exactly along the gradient vector of f, then that means the dot product is maximized. That orthogonal projection is as big as it's going to get, and that means the rate of change of the output of f is maximal in the direction of the gradient vector. That's the proof. That makes a lot of sense, and you can see it. Here I've plotted a bunch of different examples of points, and looking at the gradient vectors at those various endpoints, you can see the orthogonality. You can see that it's always moving in the direction of maximal increase of the function. Even as we're moving all of these points around, you can still see that. That's a two-dimensional picture. What happens in 3 dimensions? Well, that's a little bit harder to visualize. What I've shown on the left is one particular level set slice with the gradient vectors illustrated. In general, if you're moving around in 3D, you have a whole bunch of different level sets. You need to think of that gradient vector field as giving you a vector at every point in space. And at each such point, it is orthogonal to the associated level set surface and is pointed in a direction of maximal increase. Now let's see what happens when we look at an example involving gradients and level sets in arbitrary dimension. Consider the function f of x equals x dot x on Rn. That is the sum as I goes from 1 to n of xi squared. What is the gradient of this function? Well, it's not so bad. You can show that the gradient of f is really 2 times x. That is, in the ith component, it is 2 times xi. Now, we could write that out using summation notation and basis vectors e sub I. You should check that. But what I really want to do is think about the geometric interpretation of this. That function, the sum of xi squared, x dot x, is giving the distance to the origin squared. What are level sets of that distance squared function? They are spheres. They are n-1 dimensional spheres sitting inside of Rn, sets of points of constant distance to the origin. Now these gradient vectors are all orthogonal to these spheres. That means that they're pointing out in the radial direction, and they're pointed in a direction of maximal increase. You can see in this example, with a single level set and a two-dimensional sphere sitting in R3, the general case requires a little bit more work.